The schedule this week. Let's learn the important stuff, we always say. Embedded systems, okay? So, 2 quizzes. Today's quiz is on stick diagrams, is a really simple one. And on Wednesday, since we will cover this topic for 2 lectures, at least. So you guys will have another quiz on Wednesday. And there will be a homework 4, I haven't posted yet, right? Yeah, there will be a homework 4 on stick diagrams. So you'll know that it's pretty important, especially for manual layout in your circuits. But today's is really simple. All right. So we were talking about a couple of NMOS transistors in series, right? So now let's take a look at that really quick and why we can remove all the diffusion or the P plus or N plus terminals. So it looks like this. Four transistors. It doesn't really matter if you're using a cross to represent NMOS or a circle to represent NMOS. It doesn't matter. I couldn't even remember which one I used. But now let's just use the cross. So 4 transistors, you need 5 nodes. Okay, put them in series because it saves a lot of space, right? I got gates. 4 gates means 4 transistors. Why is that? Imagine the cross-sectional view will be this. Keep going, right? So how the circuit is connected if you look at the cross-sectional view over here. There are 2 terminals, right? But now it's getting merged. But before it's getting merged, there's a wire, right? It should be a wire because these are wires. Wires and terminals. Okay, if you merge it, what's happening is this. Since they are shorted by a wire, so we can treat them as the same voltage node. So they are the same node. So that's why we can merge it. And why is this is two channels, 2 length? It's definitely longer than 2 length, right? What is the length of the transistor? Which dimension the length? Here's the length, right? And when you are putting them in series, it's adding the length together. And these are not considered as length of the channel because these are not length of the channel. These are just the wires. So we only consider this part as the length. So which is exactly the area underneath the gate. Because only the area underneath the gate is considered as a channel. Okay, but all these are just wires. So in that case, you don't even need all these gates. So in between, what's happening is it still has the diffusion, but doesn't have the via and nodes, the metal one on the top of the via. Okay, so what's really happening here is you do have a for the layout top view, for example, right? It's separating all these areas by this diffusion, but there's no via and node and metal one on the top. But there's still diffusion in there, like P plus or N plus in there. But it's being separated by all these diffusion blocks and only leave all these separate channels in there. So they are getting all these lenses added together in series. That's what's happening. Okay, that's why the length is not changing. It's just adding all this length together. But you just have to have the gate in order to open up the wafer's channel area. Because when we do the diffusion, we have the gate on the top. That's why it blocks all the P plus or N plus materials from getting into the wafer, right? That's why it's forming a channel here. Okay. And for the AOI logic, will be the main topic here, and we have to know the AOI logic in order to draw stick diagrams. So AOI means and, or, and invert or inverter. Inverse probably. AOI. So this comes from the CMOS logic, CMOS circuits. So for example, if I draw this, 3 transistors in series, similar to this schematic, okay? 3 transistors in series, and I got 3 signals connect to the gates separately. And definitely NMOS is good at passing zeros. That's why I short the NMOS, the last one source to ground, okay? If this is the VL, so VL equals what? It doesn't work for the one logic or logic 1. Why? Because there's no VDD. You're not getting a 1 at all, right? So the only thing you can get from this circuit will be a logic 0, possibly, if you have all the transistors on. Right? If it's 1, 1, 1, then the result will be 0. That's the only definitive answer you can get from this circuit. So this is passing zeros. It's trying to pass a 0 to the output. But I have to give 1, 1, 1s. So if you give 1, 1, 1s, and from the AND logic has to be A and B and C, or it has to be all 1s at the same time. Okay? And eventually, if A and B and C's are all 1s, it's giving the zeros. That's why you have to invert it. This is A and I, right? It's AND and invert. So what about this one? VDD and VL. Still the same signal lines, A, B, and C. Apparently, this circuit cannot pass the 0 to the VL because there's no 0. Where is 0? No 0 at all, right? So the only voltage available is VDD. Okay, so it's trying to pass VDD to VL. Okay? How do you get VDD? For this one, right, they're in series, so all of them have to be 1. Have to be 1s. For this one, okay, anyone becomes 1 is going to form a channel from VDD to VL. They're in parallel, right? So anyone becomes 1 is going to pass VDD to VL. All right? So what is the logic for this? We have to draw the truth table, but if we just look at this logic, so you need a voltage 0, right? You need a 0 to turn on the PMOS, right? It could be this one becomes 0, this one becomes 0, this one becomes 0 as well. Doesn't matter. Or 2 zeros, 2 zeros, 2 zeros, or 3 zeros. Doesn't matter. It's still the same logic. Take a look. You just need one of them becomes 0, and the whole thing becomes 0, and then you invert it, and becomes 1. Why is it getting inverted? Because this guy is shorted to VDD. When you give a 0 here, you are getting a 1 out. So this circuit follows this logic expression. Same as this one, but they are doing different things. This one passes VDD to VL, and this one passes ground to VL. But they use the same logic expression. And eventually, you can combine these two circuits to 1. So here comes the conclusion. What is the result here? if I combine them. You don't trust me? Let's draw the truth table. A, B, C. VL 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay? 0, 0, 0 is giving you what? All of the NMOSes are off. PMOSes are on, so this is definitely 1, right? Well, this one. Keep in mind, you need all of them to be 1 in order to get a 0. Okay? All of them have to be 1. So all the A's have to be 1. All the inputs have to be 1 in order to turn the NMOSes at the same time. So you are getting a 0 at the output. Okay? If you have 1, 0 in the input, the result will be 1. Right? If you do the K-map, you are eventually getting out the final result, but you could also do what? How do we simplify this to a K-map? I've been doing SOPs. What about the POS? If you do all the SOPs, eventually you are finding out. Let's just do the simplification. A, B, C, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, right? So the only 0 is 1, 1, 1, but all the rest are 1s. I'm definitely complicating things, but so this one's giving you what? A naught, and this one is giving you B naught, and then you group these guys. It's giving you C naught. Did I make anything wrong here? Why it doesn't seem right? Apparently A, B, C, this shouldn't equal to this, right? Let's see. This A, B, C equals De Morgan's law, right? They're actually equal. Okay, they're actually equal. Same stuff. Do you still remember De Morgan's law? So how to remember De Morgan's law? So keep in mind these two rules, right? Split the bar and change the sign. What does that mean? So if you have, for example, A and B naught, okay, and that equals A naught or B naught. So split the bar and change the sign. You either split or merge it, okay? So change it from and to or to and. So if you do this, you treat AB as one entity, So do it once, so you're getting AB naught or C naught, and then split AB naught one more time to this. Okay, that's De Morgan's law. Keep in mind. So similarly, we can find out the NOR gate. So this is a NAND gate. It's a 3-input NAND. 3-input NAND gate. Okay, it's a 3-input NAND gate. So a 3-input NOR gate looks like this. It doesn't matter which one's A, which one's B, which one's C, they're equivalent. Okay, if you put 3 PMOS on the top in series and 3 NMOS at the bottom in parallel, eventually you are getting VL to be A or B or C bar. And here comes the conclusion. For so first it's getting inverted, right? First, for this type of circuit, it's getting inverted eventually. So you want to convert whatever logic expression in the form that you have a logic expression at the bottom and the one uniform bar on the top, just one bar on the top. Okay, and then you are looking at the logic expression at the bottom of the bar or below the bar. And if you have an OR logic, you should keep PMOSes in series and NMOSes in parallel. If it is an AND logic, you're gonna keep the PMOSes in parallel and NMOSes in series. That's the conclusion. And we'll look at more examples after this, but just to memorize it for now, or just put on the notes, so we don't have to revisit this all the time. It takes such a long time, 2-3 pages to get to this point. We can verify, use a truth table or K-map every time if you want, but we don't have to. So just memorize this conclusion for now. Then we'll look at some examples very quickly. One more thing. So you can see that the gates are being shorted together. For example, the PMOS and NMOS, they are both serving one input. Keep in mind. Before moving forward, how do we draw the stick diagram for these gates? How do we do it? So let's start with the two input NAND gate first. Start with the easier ones. This is NAND gate. It's NAND gate. How do we draw the stick diagram? So keep in mind the stick diagram represents the same layout, same structure of the layout. It's helping you to plan for the layout ahead of time, since it's so easy. How many transistors on the top? 2. So you need 3 nodes. That's the top rail, that's the bottom rail, that's the VDD, that's ground. 2 gates because I have 2 PMOS transistors. How many NMOSes? 2 as well. Okay? And you're asking, hey, these are in parallel and these are in series. How could you do the same? How do you just connect all the nodes in a line? Because we can modify the metal wires in order to make them in parallel, either in parallel or in series. And this is how we do it. So how do we make them parallel? Like I said, there are two ways to do it. You could either do this, so current flows and split and merge and come out from this metal. And these are gates. Keep in mind, these are gates. So here's the VDD, right?
The X's and the circles, are they for NMOS or PMOS?
Doesn't matter.
Doesn't matter?
Yeah.
Okay.
Usually we just keep the PMOS on the top. If you have whatever on the top, so everybody knows that it's PMOS, right? Doesn't matter. Yeah. Okay, so you have all these current from the VDD and then split in two branches and then comes down to here, these two nodes and merge to one. So it's flowing across these two channels at the same time, so they're in parallel, right? And then merged into one and go to the whatever the NMOS is over here. So the NMOSes are like this. They are in series, right? So we want to do this and connect the ground. So it directly flows through the two channels. They're in series. So there are two ways to connect it for the PMOS, and it actually matters. Can we do this? Can we connect it this way? One current comes down, split, and merge. What's the difference? Merge and go and keep going to reach the NMOS at the bottom. What's the difference though? I mean, for this example, it probably doesn't matter because the circuit is so simple. Right, but in the future, you have to consider that if you, for example, you have more nodes in the middle, and if you close it by this wire, it's give you a hard time to wire everything out from the middle. You know what I mean? So there's nothing that you need to connect it to for here because you already have this wire on the top. But in the future, you have a pretty long string of transistors, and there are a lot of nodes in the middle. And if you close it that way, you have to find a space in the middle to build the vias. It takes space. So it's better to have everything on the top, like this, and you need a space here to do all the wiring. You know, it takes a lot of space and to build the vias on the metal. Some considerations. That's why you need stick diagrams, so you can plan for all these traces ahead of time. Okay, before you mess with all these wires. Does that make sense? Okay, so this is a NAND gate layout, a stick diagram. In the future, when you are doing the layouts, you place two transistors, you'll do a wire here, and you introduce another wire here and connect two NMOS, series NMOSes at the bottom and short it to ground. What about the gates? You have A and B's, right? Even though they are equivalent, so the two parallel transistors are equivalent, doesn't matter which is which, and these are equivalent as well. However, it probably matters for the position of these two transistors because one's on the top, one's at the bottom. So in the future, if you have a bigger circuit, if you don't follow the certain order, you are not passing LVS. So the schematic or NCC, right? It's called NCC in the electric VLSI, or it's called LVS, which is layout versus schematic matching. So the position here matters. Let's just take a look at this one. So which is A, which is B? How do we connect the gates? You can see the gates are shorted together, right? And because this one got split in two branches, so these two are equivalent. Either one can be A or B, doesn't matter. But which one do we want to? So for example, if this is A, this is B. It is. You can see the position here. So when the wire comes down from the PMOS and firstly it reaches transistor A. Same thing. So when the two parallel get merged over here, firstly it reaches NMOS A, and then B. So this must be A, this must be B. If you swap them, you're not passing LVS. Makes sense, right? So this has to be A. If this is A, and you're saying, hey, these two are equivalent, doesn't really matter because they're in parallel. It reaches VDD current signal from the current from VDD reaches the two transistors at the same time. So these are equivalent. Yes, they are equivalent. However, which is better to be A? What is this wire from the middle? The node in the middle represents the P plus and the via and metal 1. That's the little node part from the library. It has the diffusion, which is P plus, and the via and the metal 1 on the top. So you can directly introduce the metal 1 from that node. So that means this is going to be what? What is this wire? So what are the wires shorting all the nodes together? You guys deserve a decent drawing here. There's nothing can be an arc in the circuit, right? In the IC. What is that wire? Metal 1. Okay, it's a metal 1. So what is this wire? It's gonna be a metal 1. Has to be metal 1. There's no poly. Poly is a gate. It's not a gate. It's a node. So node need a via to be shorted to metal 1. So this has to be metal 1. Okay? So what is a gate? Poly. It's a poly. Alright, so which one should be A, which one should be B? You want this one to be A? Okay, so now let's connect the two polys. Okay? And this has to be B. Let's connect these two polys. Oops, shorted. Same layer. Now let's drill a hole to the top, connect to metal 1 like this, and make the connections. It's very unnecessary. Let's just directly do this. Poly and poly. You're saying, hey, short it, because there's a wire here. Short it. Are they shorted? No, poly is at the bottom. This is metal 1. This is metal 1. It's okay, do this. So it's better to have this one to be A, this one to be B. Alright? Since this has to be A. Because of the label here. The label here in the schematic. And then your schematic and layout will match. Okay, it's going to pass LVS or NCC. It's going to show like ports match, topology match. Okay, show all these pleasant messages in the message window. What's next? And you need the metals for the gates, right? So that all the signal lines are shorted to metals. So in that case, you need a little poly extended to the outside of the gate area, and you have a little node which is poly to metal 1 via. Okay, and then you got a little via here in the middle, so you can connect to metal 1. And there's a little port A here. What about this guy though? You're complaining because the channel is too small, too short, and there's no enough space because the design rules has to be 1.5 lambda. So there's no space that allows me to extend this wire and make a little via here. No space. So what else I can do? Get the poly, and extend to here. No, it's getting shorted. It's shorting to this gate. So what else? Another way you can do that is extend to the other direction and making a little poly to metal 1 via. Okay? And then introduce the metal 1 wire here. It matters, it's shorting to this metal 1, right? Shorting to this metal 1. So that's not a good idea for this design. It's not good. What else we can do? Metal 2 can be an option. Let's see what we do here, what we did in the lab layouts. Probably the two port NAND gate is not a problem. Here's the NAND gate. Okay, so forming this is, imagine this is a stick diagram. You got 1, 2, 3 nodes and 2 gates. All right, let's look at the NOR gates though. The NAND gate, I don't know why the picture is not showing up. Let me refresh. Something is wrong with it. Let's look at the NOR gate instead. So the NOR gate is very similar, right? I have 2 PMOS in series and 2 NMOS in parallel at the bottom. And now the layout looks like this. So you can see there's no space in the middle, no space at all, because I have to keep the channel short. Okay, so you see that I don't even have space to keep this straight for some reason. So it doesn't look really good. But you can see definitely there's no space in the middle, right? To keep this poly to metal 1 via in the middle. So I have to extend it to the other side. And so how do we connect metal 1 to it though after everything? So you can see if I have multiple gates being shorted to the in between the same rails like this. So this is 1 gate, another gate, another gate, another gate. Okay, and they're all shorted to the same VDD and ground. So you can plan for the connections first. So highly recommend that if you have different colors of pencils, you can definitely use that to differentiate between the different layers. So know which color represents which layer. I can see these are the 4 gates. These are just inverters, and 2 NOR gates, right? 2 NOR gates because PMOS are in series. Oh, I'm not done yet. Let's see. These are XOR results, XOR outputs over here. What's a schematic? It's like this, okay, like this. And this schematic comes from the AOI logic. It's over here. So both PMOS and NMOS are in series. Oh. What's going on? I can't even do it using the desktop over here because it's just not showing anything. Okay, cool. Okay, let's take a look at this example. Okay. VDD are actually the taps. So these are N-tap or P-tap? Really quick question here for you guys. N-tap or P-tap? You just realize that all the power rails are just taps. It's unnecessary to create another metal wire just shorted to the VDD, right? Because all the N-taps are shorted to VDD and all P-taps are shorted to ground. So just directly build a via on the N-tap over here, build a via, actually multiple vias, and short metal 1, have a little metal 1 layer on the top of the via to form the top rail, which is VDD. Yeah, you have to short all the N plus or N taps to VDD anyway, right? Similarly to all these P types, so the P tab, the little P plus in the NMOS transistors are shorted to ground because you have to short the P well or P sub to the lowest the potential of the circuit anyway. So first, when you are building a circuit, first you have to define a certain gap in between these two power rails, VDD and ground, okay, and then start placing all these components in the middle. Right. So see here, it's difficult to, because all these drains are shorted by metal ones. So in that case, if you want to have any signals being shorted in between these gates, you just have to use metal 2. There's no way that I can use a single metal layer to make all the connections. They are going to be shorted together. Do we need the metal 3 for now? Probably not. Not that complicated. But eventually you will need a metal 3 sooner or later. If you look at this one, it's getting more complicated, and you will need metal 3, which is a yellow one over here. You only have 3 metal layers. So you can imagine if you have more metal layers, it's getting easier. It's getting easier to finish the layout within a certain area, right? And more metal layers will let you keep your circuits more compact as well. You don't have to worry about any of the short circuits. You can make it more compact. Right. Let me give you more examples. Any questions on this by far? No? One more example, we'll do our quiz. Okay?
We do the one on the left this way, not a stick diagram. For it to be a stick diagram, it has to be cross and circles.
Have to cross? No, just the stick diagrams. No cross sectional. Is that a question?
No, I was just saying like, yeah.
Yeah. So you have to make the connections.
But like that's called the stick diagram, not this one.
Yeah, this is stick diagram. This is AOI logic. This is AOI schematic. Okay. It'll be sweet. It's always the NAND gates, right? But there will be some arbitrary logic expressions to ask you guys to work on. So first, you have to convert it to the AOI. Keep in mind, you have to inverse. So eventually, it has to have a bar on the top. So if it doesn't have a bar, we just have to add a bar on the top. If you add a bar, you change the logic. You have to add 2 bars. It's not changing the logic. And remember De Morgan's law. Split the bar, change the sign. So keep the top bar on the top, and then just look at this circuit. Split the bar and change the sign. So you are getting this. Split the red bar and change the sign. And this becomes A and B not or C not bar. Right? Next, we can start working on the schematic. Because I told you that if you have an AND logic, you want to keep the PMOSes in parallel in series for the AND logic. Think about the NAND gate. In parallel, PMOS are in parallel for the AND logic. Okay, so for A and B, C, B not, C not, so they have to be in parallel, which is A has to be here, and for B and C, B not or C not, they have to be in series like this. Always think about the NAND gate and NOR gate examples. So here's VDD. For the bottom, OR logic is keeping the signals in parallel, and AND logic keeping the signals in series. And we'll work on the stick diagram of this logic or of this circuit next time on Wednesday. And there will be more examples covered on Wednesday. But today's quiz is way easier than this. Yeah, since from the inverters quiz, I found out you couldn't even draw the transistors correctly. So I'm trying to make it super simple. Two inputs, yes.